Yeah. So, in the previous class, we have understood the essence of the course. Why we want to study the chemical gas engineering. Fine. Why we want to study the chemical gas engineering. I just given a brief overview of the course and the essence, not the importance. Fine. Yes, get it. Please leave to the class 5 minutes prior. Okay? Please unnecessarily disturb me as well as disturb all the class. Okay. So, what I given the themes of the course yesterday, last time, the last class is why do we need to study the course? Chemical reaction engineering. What is the essence of learning the course? Can anyone? What is the essence of learning this course? Why we need to study this course?
To control it.
Yes. Perhaps if you understand the reaction in a better way, you can control or you can manipulate or sometimes you may increase or you may decrease. That's what the essence of this course is. Fine. Now let's take for example when we write A plus B as something like C, the product, this is what the reaction we thought of. What is this meaning of this A plus B giving rise to C?
Different reactions to combine to form product.
That means any two entities or any two substances, when they interact, when they combine to form a product, this is what we call as a definition of chemical reaction. Fine. But ultimately, if you look at, for example, take an example of this ammonia formation.
Two energies.
So nitrogen in the gaseous state, hydrogen in the gaseous state, forms ammonia. Maybe in the liquid or a solid, and whichever form which we want. Now, if I talk about, maybe we can put in the gaseous form also. Just look at the case. What we written A plus B giving us to C is not as simple as what we thought. For the sake of this example, nitrogen, that means what? NN. Hydrogen means H. So in the sense why I am writing like this is, when nitrogen reacting with hydrogen to form ammonia, ultimately what happens is, this nitrogen molecules has to react with hydrogen molecules to form ammonia. Now, how it will react? If you look at very carefully, this nitrogen has a bond, maybe single bond, double bond, or triple bond. Hydrogen also has some bond. That means a bond between the two atoms. Similarly, ammonia has some bonding. Now, ultimately, what will happen? This bond has to be broken down. Fine. Similarly, this bond has to be broken down. Then this N and H should interact, and finally, this N should be reacted with the three hydrogen molecules, three atoms to form ammonia. Now, ultimately, what is happening? There is bond breaking, is it not? And there is some new bond forming. Understood now? So it is not as simple as just writing A plus B giving rise C. It is when a reaction occurs means there is some bonds are breaking down and some new bonds are forming. Now ultimately to break the bond or to form a new bond, what is needed? It is needed is first of all the collisions. Is it not? This nitrogen has to collide with hydrogen. It has to collide, it has to react, it has to interact. So this collisions matters a lot to form a new bond. Because it has to be ruptured first. This bond has to be broken down. And this nitrogen should interact or collide with hydrogen. Then only this interaction will happen, and then nitrogen will form a bond with hydrogen to form ammonia. So the effective number of collisions will only leave the product. Why I am saying is effective number of collisions. Effective number of collisions. Because all the collisions will not give the product. All the collisions will not give you the product. Only the effective number of collisions. Because the collision will also be in certain direction only. Then only we will get a product. Okay. So or otherwise I will give you some pictorial way or some example. Let's take two glasses. So let us have some water in the board. Now I am adding in one case sugar cube. In another case I am adding sugar powder. Maybe equal quantity, let us say some 10 grams. Cube means what? This is sugar cubes. You know sugar cubes. If you go to hotel, they will give, maybe in 5-star hotel. Sugar powder, you know. Every in home we have the sugar powder. We will take from school. So maybe the same quantity I am adding cubes in one of the glass and powder in another glass. Now you tell me in which glass of water sugar dissolves faster? Powder. Why the reason?
So because it is a powder.
Just sit down. Don't be formal. Yeah.
So maybe the intermolecular forces between the powder is very weak than in the solid.
No.
Molecules are not tightly bound.
But there is no need for collision of sugar intermolecular bonds because it is powder. That's why it can dissolve in water fastly.
No.
The surface area of
Yeah, the concept is surface area. He is correct. But before going to the surface area concept, let us understand what is this sugar dissolution. See, everything we should understand in a little bit depth of knowledge. Just like a layman we cannot understand. When you add sugar, when you stir with some spoon, it is dissolved. Now, what is exactly mean by dissolution or solubilization? What is the interaction? What is sugar? Sugar is sucrose. What is sucrose? In last class I told you.
Glucose.
It's a combination of glucose and fructose. So you know the glucose structure. So this is the one molecule of glucose. Maybe if I rearrange the structure, I will get the fructose. So a glucose and a fructose linked with some small bond is called sucrose. That means a sugar molecule. So this is the entirely a sugar. Fine. Now what is I am interacting? I am interacting sugar with water. What is water? H2O. Is it not H2O? Now this H2O has to be interacted with the sugar molecule. Now when it interacts, it dissolves we are talking about. That means it solubilizes. Means what is happening? What is happening? Water is a polar molecule. What is polar molecule? What is polar molecule? Which has certain dipole moment. What is dipole moment? Any entity, if it has been connected with different electronegativities. What is electronegativity? So it's a chain of questions. So if you don't know the fundamentals of physics or chemistry, you will lack of all these concepts. So I didn't call a very high-end question. Electronegativity, polar, dipole moment, which you come across in 10+2. So water is a polar molecule. I'm just leaving to you because if you want to brush up, you will understand the concepts. Otherwise, you will be there only, and I will be here only. So polar molecules, so slightly negative charge will be there on the oxygen, slightly positive charge will be there on the hydrogen. In the similar case with this also, so there are certain polar groups, charges, where this water molecule, the gaps will be filled by the sugar molecules. So this sucrose or glucose or fructose or whichever solid molecules will come and occupy the solvent molecules. The solvent here is water. So wherever the gaps are there in the solvent molecule, the spaces have been occupied by the opposite and charged molecule. So here the sucrose having different charges will be attached to the opposite charge of the water molecule. So because of this attraction is overcoming the intermolecular force of the sucrose molecule, the bonds will be cleavage. So when the bonds will be cleavage, it means what? It is slightly dissolving in your solvent. Understand the concept of what is sugar is dissolving in the water? Sugar is dissolving in the water means solid molecules, maybe in the case of sugar here, sucrose molecules are occupying the sides of the water, the spaces. How it will occupy? Because it is attracting by the opposite polar forces. Because oxygen has negative charge, so the positive charge wherever happen to be in the sucrose molecule will be getting occupied. So this attraction pulling. So when this pulling is more, automatically some bonds will be cleaved. So when bonds will be cleaved, it slightly dissolves. So it slowly dissolves in the water. Understood now? So sugar water లో డిజాల్వ్ అవుతుందంటే ఏమవుతుంది? షుగర్ లో ఉన్న సుక్రోజ్ మాలిక్యూల్స్ వాటర్ లో ఉన్న హెచ్ లో ఉన్న గ్యాప్స్ ని ఫిల్ చేస్తూ కూర్చొని బాండ్స్ బ్రేక్ అయ్యి డిజల్యూట్ అవుతుంది. దట్ ఇస్ వాట్ ద రియాక్షన్ బిట్వీన్ షుగర్ అండ్ వాటర్. నౌ హియర్ ఐ ఆస్క్ ద క్వశ్చన్, వెన్ ఐ కీప్ ఎ క్యూబ్ it is taking more time, but when I keep sugar as a powder of the same quantity, but it reacts very fastly and dissolves very fastly. So what is the reason? Whatever he said is correct. The surface area, here the surface area is more, here the surface area is less. How we are saying surface area is more here and surface area is less here? See, remember, for anything to reaction there should be some platform. Okay, for example in this case sugar molecule and water molecule has to be reacted or has to be occupied, so there should be some space available, then only they will sit, react and then leave out. So here in this case, let us take here in this case a cube. So I have some water molecules. Is it not? In this case, I have some water molecules. That means what? These water molecules may sit on the sugar cube in this side, or this side, or this side, and slightly they will occupy the polar groups and then dissolve. Fine. So there are only 4 chances of water molecules to sit on the cube: front face, back face, or side faces. But here in this case, I have sugar powders, almost small entities. So when I have the size is very small means what? More surface. Here only 4 sides are available for sitting. But in this case powder means almost a spherical end. So small entity. So more surface. So more water molecules can sit. More reaction, more dissolution, quicker. Got now? So sugar powder has more surface area for reaction. More surface area means, see, this is entire surface area is available in this case. In this case, only very small cube surface area is available. So if more surface area is available, more water molecules will sit, more reaction can take place, more solubilization, more dissolution. Clear now? So why sugar cube dissolves slowly compared to sugar powder in this case? Now let us take same case. Instead of cold water, I get hot water. What will happen? Or just leave about this, because you already understood this is waste now. Because the surface area is less, that is waste. Now take cold water and hot water. I have a glass of cold water, I have a glass of hot water. Now I add in the sugar powder only, because sugar powder has more surface area. We understood the concept now. So in which case the dissolution is faster? Hot water. Why? See, in this glass also water is there. In this glass also water is there. But only thing is, this water is at cold temperature. This water is at hot temperature or little bit higher temperature. Then why sugar quickly dissolves here? Why not in this case?
Some energy is given.
Some
Energy.
some energy given to whom?
The
Water molecules. This water molecule is already given some heat means what? Some additional energy I am giving to this. See the same example. If you are like this, if I won't give anything, will you work? If I give some energy, maybe in the form of some food, maybe in the form of some cash, definitely you will work because your energy is higher compared to the older state. Similarly, the water molecules in the left glass, which are at the cold, have minimal energy. But if the same glass of water, if I give some temperature, if I give some heat energy, what will happen? So the effective number of collisions here will be more because the molecular motion is more because the energy is associated. I already given some energy, so there will be more molecular motion. More water molecules tend to vibrate, tend to react with the sugar molecules because already some energy is given. Clear now? So that means what? Here temperature plays a crucial role. Is it not? In the left case there is cold, but in the right case there is temperature I given. Some temperature, let us say I have given some 50 degrees centigrade. So if the temperature is raised, the molecules get energized themselves. So more molecular motion. More molecular motion means what? More collisions. More collisions with what? Sugar. So water, sugar, more collisions because the water is already energized because I given some external energy of heat. So more molecular motion, more collisions. I already told more effective number of collisions will lead to product. So that's why hot water, the sugar dissolution is much faster than the reaction in the cold water. So what is the essence of this example? Temperature. If I raise the temperature, the speed of reaction is rising. Is it not the speed of reaction here? What is the speed of reaction here? Dissolution. In our case, dissolution, solubilization. So the temperature is the one factor which influences the reaction. Understood now? Understood now? Now another factor which influences is concentration. How? For example, same case. I have some 10 molecules of A, some 20 molecules of B. When I react, I got some product C, maybe of some 30 or 40, whatever it may be. Fine. Now if I increase molecules of A to be some 30 and molecules of B to be 40, will the same product of C will form or the product will be more?
Product will be more.
Will the speed of the reaction be more or less?
Less.
Okay, come to normal question. I given this room. I given only 3 people to clean the room. I given this entire room. I given only 3 persons to clean the room. How much it will take? Maybe it will take some half an hour or 1 hour. The speed of the 3 persons to clean the room is just 1 hour. Let us suppose instead of 3 I have given 10 persons to clean the same room. Will it be same 1 hour? How much it will take? Less than 1 hour. Maybe in half an hour it may complete or maybe in 20 minutes it may complete. If I increase 20 persons in the same classroom to clean,
10 minutes. 10 minutes.
so what I am doing here, I am increasing the number of molecules, I am increasing the number of reactants, I am increasing the concentration, I am increasing the composition. If I increase the composition, the speed of the reaction is increasing, is it not? Earlier it is taking 1 hour, but now it is half an hour they are completing. 10 people are there. Only 15 minutes, 20 people are completing. Just in 5 minutes, 100 people are completing. So the more number of molecules, more number of collisions, more product at the same time, more speed up of the reaction. Only 3 people will take 1 hour time. 10 people will take half an hour time. 20 people will take 20 minutes. 100 people will take only 5 minutes. So the speed is quickly rising if more number of atoms, persons, molecules, ions, whichever may be the entity. Understood now? More numbers if I involve, the speed is increasing. So, composition or concentration is another term which is influencing your reaction. Okay? So, temperature rises, reaction speed rises. Concentration or composition rises, the reaction speeds are rising. Now, what is speed now? We should define the speed. See, speed is a term where we use in physics, but we cannot use in reaction engineering. Speed or velocity are the terms which we use in physics, but in reaction engineering we cannot use the terms called speed or velocity. So what is the term that we use for reaction engineering? Rate. So very good. So we write rate of the reaction. Instead of speed, we write rate of the reaction. How do we define rate of a reaction? Now we should understand what is the rate we should define now. You understood there are number of molecules that are colliding. So this effective number of collisions leading to some product. Now what? How I define the rate of a reaction? Or earlier, what is the speed of reaction? How do we define? Let us take an example that in the laboratory you are taking some beaker. Maybe in intermediate stage you have taken some beaker and you added some component A, added some component B, and you are stirring. Maybe you are shaking. Sometimes you will break also. That is leave about it. But when you take a beaker, when you add some two ingredients, when you shake it, you are supposed to be there. Two reactants are reacting. So there is certain volume involved, and you are seeing certain time of reaction. Maybe in 10 minutes you may say observe some new product come, new color come, new flavor come, new smell come, new order will come. You observe. That means what? There is a time factor involved. There is a volume involved because we are taking only this much of volume, maybe 500 ml flask or 100 ml flask or 1000 ml flask. In that volume only we are reacting the ingredients. So here the volume is involved, the time is involved. In that volume, in that time, we are seeing the reaction rate, whether it is fast or whether it is slow. So the reaction rate we define in terms of volume and the time. So in a particular unit volume, for particular time period, how many moles of reactant is disappeared? Because A is disappearing, is it not? Initially A is there, initially B is there, but ultimately when you look at the product, there is no A here and there is no B here. A new product C has formed. That means what? The reaction rates can be written in terms of reactants or products. In how we will write the number of moles that is disappeared or the number of moles that is formed. So I will write the rate as number of moles of reactants disappearance, or sometimes I will write products formed because we are looking at reaction. Sometimes this is disappearing, or sometimes this is forming. I may write reaction rate in any way. Either the reactants to be disappeared or the products to be formed, or unit volume or unit time. Because in a particular time, in a particular volume, we are observing the reaction rates. So the number of moles of reactants disappearance or the number of moles of product formation per unit volume per unit time is the reaction rate. Okay, so there is no term called speed. We should now distinguish ourselves in reaction in kinetics. We talk about the reaction rates. So reaction rate is the number of moles of reactant disappeared. Is it not disappearance?
Yes, sir.
Initially A is there, but finally I am not seeing A. Initially B is there, but I am not seeing B here. So either disappearance or formation. Initially C is not there. You see, C has formed. C has formed. New appearance. Here disappearance, it is appearance. So I may write in terms of reactants or products the reaction rates. Okay. But the usual convention is whenever you write rate, the rate expression always return in terms of concentration of reactants only. A more usual convention of writing the reaction rate expressions in terms of concentration of the reactants only. Now, before going to that part, let us think of the previous example. As I told, your reaction rate has been influenced by two main important factors. One is the temperature, other is the composition. So, I will always write rate as a function of temperature dependent term comma concentration dependent term. Why I written only two terms here? Because specifically we discussed it. When I increase the temperature, the effective number of collisions increasing because molecules are getting energized. More number of molecular motions, more number of collisions, more reaction rates. We have seen. Similarly, example of concentration, more number of molecules involved. Case of example of 3%, 100%, 50%. So more number of molecules, more number of collisions, more reaction rate. So reaction rate is function of temperature dependent term, that is T, and concentration dependent term, that is C. So we will write rate equal to this temperature dependent term is replaced with some K called rate constant, and this concentration dependent term has some C. So we will write like this, always rate equal to temperature dependent term. We will write as K. This is for rate constant. We again will discuss what is rate constant. But time being, I am saying rate constant, and C is concentration. Okay. So what this user convention says is always write rate expressions in terms of reactants only. For example, if I write A as to B the reaction, the rate of A is given as K times concentration of A. Because the convention is to write the rate expression as rate constant multiplied with the concentration. How it has emerged? Because it has emerged that it is only function of temperature dependent term and concentration dependent term. So this temperature dependent term is replaced with K, this concentration dependent term is replaced with C. So when a reaction is given, so I will write rate expression. For example, in this case A gives rise to B, I will write rate expression of for A as rate constant into concentration of A only, not B. Because what is saying? Write always in terms of concentration of the reactants. So for example, now what is the rate expression? K into concentration of A, there is one more concentration. For reactants I am talking about, I am not looking at the product. Product may be whatever it is. But when I write the rate expression, always we will keep in the mind of concentration of the reactants only. I will write in terms of B. Clear now? But there is one more terminology. What is terminology? Always keep reactants rate with a negative sign and the products rate positive. One more convention is when you write the rate expression, write the rate of the reactants with a negative sign. Product with a positive sign. Why this negative sign, positive sign comes into picture? Because reactants are always consumed. Is it not? See, initially if I write the expression A plus B, in starting A will be there, but after some time A will not be there, it will be disappear. That means it is consumed, it is completely lavishing. So that's why it is called a negative sign. But when the product has come, it has emerged out, it has formed, so represent with plus sign. So if I write rate expression, because here A is reactant, I will always designate with minus sign. Because A is consumed, it will not be there. After end of the reaction, A will not come out. There is a new product will come. That is called B. So write always in terms of reaction rates. Whenever the reactant is there, keep a negative sign. Whenever product is there, keep a positive sign. Clear now? Clear now? So what I discussed till this part? I just discussed what is a reaction rate. Reaction rate is moles of reactant disappeared or moles of product formed per unit volume per unit time. So there is a convention of writing the rate expression for reactant concentrations only with a convention of a negative sign for the reactant, positive sign for the products. Now this rate expression which we usually write R is equal to the definition which I have written here. Rate is equal to moles. For example, for I component I am writing moles of I disappeared per unit volume per unit time. So this is what the rate I am writing for fluid. If I am talking about a case of fluid, I will take unit volume of fluid. What is fluid? What is fluid? Fluid may be gas or liquid. You know that. Solid is solid phase, which is different from the fluid phase. Now, this expression of moles of I disappeared or sometimes a product form per unit volume per time. In case of fluid, I will take unit volume of the fluid. But the same definition is applicable for different types of reactions. There may be fluid solid reactions, there may be solid liquid reactions, there may be gaseous reactions. For every type of reaction scheme, this expression is little bit changed. That means the down form will be changed. I am talking about only unit volume of the fluid and type here. If I talk unit mass of the fluid, I will take unit mass. If I take unit surface area, I will take unit surface area. So note it down the expression so that we will discuss once. So that the fluid case you have written. Let us write in case of solid and fluid solid systems. In case of fluid solid systems, this rate is equal to same moles of I form. Maybe if I write minus, it may be okay. If I won't write minus, I should write form, because as I told, reactants with minus sign, product with plus sign. So form means product, so I can use plus sign. So moles of I formed per moles mass of solid per time. In case of gas solid systems, this rate of I is equal to same thing, moles of I formed per surface of solid into time. In case of volume, in case of same gas solid, I take unit volume of the solid. So sometimes I will write moles of I form volume of solid. Sometimes I may take unit volume of reactor. So I will write moles of I formed. So rate of I is equal to moles of I formed per volume of reactor per time. So what are the expressions? The expressions are similar only. Only thing is the denominator changes. So Ri is equal to 1 by V dNi by dt. dNi means number of moles of I formed. Okay, number of moles of I formed. Here also Ri is equal to 1 by W dNi by dt. For unit surface, Ri is equal to 1 by S into dNi by dt. For volume of solid, maybe 1 by volume of solid, maybe I will write with S here, suffix, so that volume of solid into dNi by dt. Or here in this case, Ri is equal to maybe volume of the reactor I will replace with VR into dNi by dt. So this dNi means number of moles of I by dt means per time. So the number of moles of I formed per unit volume of the reactor or mass of the solid or surface of the solid or volume of the solid or volume of the reactor. The expression remains same. Only thing is in which perspective you are finding the rate. In case of fluid solid reactions, you have to use mass of the solid into account, because you take some mass of the solid, on that mass of the solid only the reaction will occur. So your entity, your domain is mass of the solid. So you have to estimate the reaction rates in that mass of the solid only, not on the volume. In our first case, in our first notion, we always take a beaker, then we will pour some reactants, then we will do reaction. That is correct. So what is the reaction rate? In terms of volume only. But certainly not all cases you take the volume. Sometimes your catalyst is very small. Your catalyst is very small. So your catalyst surface area plays important role. Your mass is plays important role. So you have to account that mass or the surface area or the reactor volumes. So that's where the reaction rates are little bit changed. But the concept is same. What is the moles that is forming or disappearing per unit time? Is it clear? Is it clear? For example, if you take a corrosion reactions are always localized site reactions. Corrosion reactions are localized site reactions. Means what? In only certain site only the corrosion takes place. You look at any iron piece. If you look at any iron piece, corrosion will not be uniformly on the entire surface. Only at specific locations only corrosion will take place. That means what? In entire bar of the metal, only this area is corroded. What do you mean by this area is corroded? Means this certain area only affected. So I have to account the reaction rates in this area only, not entire area. So I have to take the surface area into account. Clear? So whether I to take the surface, whether I to take the mass, whether I take the volume, or entirely I take the volume of the reactor, that's our wish. Depending on the solid fluid, gas solid, or fluid solid, whichever the reaction scheme. Clear now? Okay. Now, so let's go to the previous concept. We have defined the classification of the reactions in the first class. How we classify the reactions? Homogeneous, heterogeneous. So depending on the phases involved, I defined as homogeneous, heterogeneous. Understood? Depending on the phases involved. So if the reaction is going in only one phase, I stated as homogeneous reaction. If the reaction is going in multiple number of phases, heterogeneous. But now look at other classification. So one I defined based on the number of phases as homogeneous. And I given examples also. Homogeneous reactions, single phase reactions. What is the best example I can give? Alcohol water mixer. Both are single phase. I given and I asked you to write also. Some of the reactions you write it on the notebook I told you. Okay. Now this is classification based on the number of phases. Direction of the reaction. Direction of the reaction. Sometimes what will happen is reactions will go in only one direction till end. Reactions will go in one direction till end. Those are called irreversible reactions. Irreversible reactions. Sometimes reactions will go front end and then back end. Will move forward and then backward depending on the product concentrations, depending on the reactant concentrations. Those are called reversible reactions. So you may have seen a lot of examples for irreversible and reversible. Okay? Is it not?
Yes, sir.
Okay? So there are a lot of reactions. Depending on progress of the reaction, maybe non-catalytic or catalytic. Now what is non-catalytic and catalytic? Sometimes we need a catalyst
To increase the rate.
to increase the reaction rates of the reaction. Best example is formation of water molecule. How water molecule is formed? When I react hydrogen with oxygen, I'll get water molecule. But this reaction is extremely slow. Extremely slow. This reaction is extremely slow. That means what? When I have a hydrogen gas, when I have an oxygen gas, if I react, I should get water. But it will not happen. You try it. I can give you the hydrogen cylinder to you and the oxygen cylinder to you. You open it and see whether oxygen water molecules are forming or not. It will never form. Because this reaction of hydrogen with half molecule of oxygen to form H2O is extremely slow reaction. But in the same reaction, if I keep some platinum as a catalyst, this will form. So this platinum catalyst will influence the reaction rates. So the reaction of forming the water molecule is faster in presence of catalyst called platinum. So catalytic, non-catalytic. So that means without any catalyst, with catalyst. So the reactions are classified based on the progress of the reaction, whether it is catalyst or non-catalyst. Then another category is nature or steps involved. As again two classifications. One is elementary, other is non-elementary. Elementary reactions, non-elementary reactions. What is this classification of reactions? Elementary reactions are one where the rate expression is in line with stoichiometric coefficient or rate expression is corresponds to, I can use the word called corresponds. Rate expression corresponds to stoichiometric equation is called elementary, or rate expression does not correspond to stoichiometric equation is called non-elementary. Now what is this corresponds or not corresponds? So for example, if I take any reaction, for example in this case A gives rise to B, what is the rate expression I have written? Minus RA is equal to K into CA. Already we have written. Why I have written K into CA? Why I have written K into CA? Rate as? Because always rates are functions of temperature dependent term and concentration dependent terms. Temperature dependent term is replaced with K called rate constant. Concentration dependent term is replaced with C. I am talking about component A. So I have written component A as CA. I written minus because A is reactant which will disappear, which will consume. So I written minus RA. So whenever rate expression corresponds to stoichiometric coefficient, then it is called elementary. What is this correspondence? For example, how many moles of A used here?
1.
What is the power of Ca? Nothing is means 1. So this 1 is corresponds to this 1. So the rate expression is correspond to stoichiometric equation. Or if I take 2A, if I got 2 here, then it is elementary. Because it says rate expression should correspond to the stoichiometric equation. How many number of moles are used? If it is reflecting in the rate expression, then it is elementary. If it is not reflecting, for example, like this, now this is not elementary. This will comes under non-elementary because it is not corresponding. Clear now? What is elementary? What is non-elementary? Elementary means this your rate expression should correspond to the stoichiometric equation. This is my stoichiometric equation. This is my rate expression. I have to look at the stoichiometric equation and the rate expression. Is it corresponding? If it is corresponding, then it is called elementary. No, non-elementary. In another way, I can define elementary and non-elementary as single step reaction as elementary, multi-step reaction as non-elementary. That means all the elementary reactions will go in only single step. That means if I write the process, the reactants will come only passing the activated complex to the product. Single step. In just in one step the reaction will happen. But in non-elementary, there will be multiple number of steps. This has to cross this barrier, one more barrier to ultimately get to product from the reactant. It has to cross this much number of barriers. So this much number of multiple steps to form product P. This is called non-elementary. In any way you can define. Elementary can be defined as a single step. Non-elementary can be defined as a multiple step. That means same A gives rise P only. Same A gives rise P only. Here in just one step we got P. By crossing the barrier you got P. But here in the same gives rise P, there are number of barriers it has to cross to get the P. More number of intermediates has formed. More number of intermediates are formed from A to get the product P. That is called non-elementary reaction, multiple step reaction. Or we can define as corresponds to stoichiometry, does not correspond to stoichiometry. For example, I can give you the best example for this. H2 plus Br2 gives rise to HBr. The rate expression is equal to K times concentration of HBr by K times concentration of H2 plus K times concentration of Br2 to the power of half. Now this is the rate expression, this is the stoichiometric equation. Is there matching? I told you the definition. If the rate expression corresponds to stoichiometry, it is called elementary. Now look at the stoichiometric equation, look at the rate expression. What is the number of moles here? 1. So it should reflect as 1. But it is reflecting as 1 by 2 here, 1 here in the denominator, 1 more 1 in the numerator, so there is no correspondence at all. So the rate expression is not corresponds to the stoichiometric equation, so that's why it is called non-elementary. If the rate expression is corresponds, that's what I written. For example, A gives rise B. The rate, if I write minus R is equal to K times Ca. So only one more is used, only one is there in the concentration power. In any way, you can define elementary, non-elementary. Understood? Okay? Now, another term we have to define at this juncture is molecularity. Molecularity is the number of molecules involved in the reaction. Number of molecules involved in the reaction is called molecularity. And one more term I have to define is order of the reaction. Order of the reaction is the concentrations powers to it is raised. The order of the reaction is the concentration powers to it is raised. That means here in this case, for example, A 1 mole is used, only the power is 1. For example, 2 moles used, power is 2. So this 2 or 1, the concentration power is called the order of the reaction. So if I write rate as minus RA is equal to K into Ca power n, this n is called order of the reaction. Concentration to the powers to which the concentrations are raised. The powers to which the concentrations are raised is called order of the reaction. So if n is 1, first order reaction, n is 2, second order reaction, n is 0, zero order reaction. So the concentrations, how much power it is raised is called order. So what is molecularity? The number of molecules involved in reaction. How many number of molecules involved? 2. So the molecularity is 2. 1, molecularity is 1. For example, A plus B gives rise C. What is the molecularity? A plus B gives rise C. What is the molecularity? What is molecularity definition? Number of molecules involved in the reaction. So how many number of molecules involved? One molecule of A, one molecule of B. Total is 2. Molecularity is 2. So molecularity is defined, order is defined, reaction rate is defined. Okay? Now note down. Note down. N2O5 gives rise. N2O5 gives rise. N2O4 plus half O2. H2O2 gives rise. H2O plus half O2. 2HI gives rise. H2 plus I2. 2NO plus O2 gives rise. 2NO2. So write down the molecularity of these reactions. Molecularity of these reactions. What is the molecularity of this first reaction? How many molecules involved? Only one molecule of nitrogen trioxide, N2O5, pentoxide. How many molecules involved here? So molecularity 1. How many molecules involved here? 2 molecules, because 2HI, 2 moles of HI, the stoichiometric coefficient is 2. That means 2 number, that means 1 HI, 1 HI. So 2 molecules are involved in the reaction. So molecularity is 2. What is the molecularity? 3. Because 2 molecules of NO and 1 molecule of O2. So NO, O2. That means total 3. So molecularity is 3. Okay. Now write rate expressions for the following reactions. Write rate expressions for the following reactions. So I told you how to write rate expressions. Now you write the rate expressions. I am just giving the reactions. 2A gives rise to R. A gives rise R. B plus 2D gives rise 3T. For this reaction, I want rates of B, D and T. And relation between them. Now, what is the rate expression for the first reaction?
Minus R.
Jahnavi. Madhuri. So, what is the rate expression for the first reaction? చెప్పండి తప్పైనా నేను చెప్తాను చెప్పండి. How we will write the rate expression? See, I told you the rate expression is rate constant multiplied the concentration term, because temperature dependent term is replaced with K, concentration dependent replaced with concentration C. So that's all the rate. But when you are writing the rate, we always keep in the mind, for reactants keep minus sign, products keep plus sign. So I am writing the rate expression keeping only for the concentration of reactants we have to write. So RA, because A is in the reactant side and B is in minus side, so minus RA is equal to K times concentration of A, but the 2 moles are used. So this minus sign may be here or here, whichever may be possible. You can write it. Or RA, you can keep minus here. Or always keep writing. Now for the second reaction,
Minus
K into CA. Now the third case. So here we want rate of B, rate of D, rate of T and the relation.
minus RB equals to KCC.
Janvi.
RB is equal to minus K into
Wait a minute. RB is equal to
minus K into
K into CB.
C square. Minus
See,
RB.
you are missing the logic. What I told the logic, rate can be written as rate constant multiplied by the concentration of the reactants. Here 2 reactants are there.
Square.
Clear? So don't mess up only at CB. Because one more reactant is there. I have to represent the rate of concentration of the reactants. Is it clear? So minus RB. RB is minus or plus? Maybe she has kept here, but what it may be, either right here or here, but B should be written with minus because it is in the reactants, not on the product. Clear? Now what is RD?
Minus RD is equal to KCD square.
Maybe, yeah.
Minus RD is equals to
Yes.
KCD square CB.
K?
CD square
Ah.
CB.
Whichever it may be, either CD square or CD square CB, whichever does not matter. Writing in terms of reactants. D is also reactant, so keep minus sign. Either here or here. Nothing matters. Clear? Now what is RT?
KCD.
So because T is the product,
No minus.
I write in terms of concentrations only. I cannot go with the product concentration. I told you, write expressions always in terms of reactant concentrations. Only CD square only. But because T is a product, keep it plus sign. Got now?
Yes.
So little bit we will do in the next class so that some of the concepts will be very clear. I just given a glimpse only. Order I define, word lot I define, rate expression define. I asked you to write something. In the next class we will go little bit further. Okay?